Welcome back, students. In the last chapter, we studied the electrostatics, charges and field. There only we understood the meaning of electrostatics, that means electrons are at rest. The next thing is we studied when the electric charges are placed, they produce effective field around it, and that is called as electric field. Today, we are studying some more important concepts of the same innate electrostatics with a new chapter called as electrostatic potential and capacitance. Already we understood the meaning of electrostatics. The meaning of electrostatics is electrons at rest. Let me understand the meaning of potential. The dictionary meaning of potential is stored. Something which is stored is called as potential. Why the word potential is inculcated or merged with the word called electrostatics? Is there any relation? Yes, there is a relation. What is that relation? Let us discuss the Coulomb's law, which we have studied already in the previous chapter. Let me consider 2-point charges plus Q and plus Q. Let me call as Q1 and Q2, and they are separated by a distance of say R. If we recall the properties of electric charges, we have a situation here, positive charge. So positive charge repel each other. So now the electrostatic force between them is what? Repulsive. Suppose if I want to decrease the distance between these two charges, that means this little r or small r should be reduced. If I want to reduce, that means either the charge Q2 or the charge Q1 should be carried from one place to another place. But the question is, the Q1 is producing the electric field which is radially outward, and that electric field is repelling the charge Q2 which is coming towards Q1 when we are decreasing the value of R. So now, to overcome from the electrostatic force produced by the charge Q1, some work has to be done. While carrying the charge Q2 from the point, say now I will call it as A and this is B, and carrying the charge from B to A. That means, so in order to overcome from the electrostatic force produced by the charge Q1, I need to bring the charge Q2 with a higher force. When we are bringing the charge with a higher force, some work has to be done, and that work done is itself is referred as the stored energy in the charge Q2, or in a simple way we can call as a work is done by the charge Q2, and that is stored in the form of potential in the charge Q2 or potential energy in the charge Q2. Friends, instead of keeping these two charges at a smaller distance, say R, suppose if I separate them at a larger distance, let me say we have a charge plus Q here, say point charge, and I will place another charge, say unit positive charge, UPC, and the distance between them is infinite. Even this condition also, the charge positive or positive charge is producing the electric field which is radially outward, and the electric force in this direction, and I am decreasing the distance infinite to a small distance, say any r or x. In that time, I am bringing this positive charge from infinity against to the electric field produced by the point charge plus Q. So when I bring the unit positive charge from infinity to the point, say now I will consider an intermediate point, say P, at some distance, say R. So now this is point P, this distance is R. So now earlier the distance between the point charge and the UPC was infinite. I am decreasing the distance between the point charge and the UPC from infinity to the little r. At that time, I had to bring this UPC from infinity to this point. While bringing, I had to do some work because this is producing the electric field which is radially outward, This is also a positive charge, experiences the repulsive force due to this plus charge Q. Hence, work has to be done, and that itself is termed as electric potential, and that is explained in the definition. What I have done here, work has to be done. At what condition work has to be done? In bringing the UPC, in carrying the UPC. From where we are bringing? From the infinitive. From where to where we are bringing? To that point. How we are bringing? Against to the electric field. That only we are defining in a proper manner. Electrostatic potential at any point in an electric field is defined as work done in carrying a unit positive charge or UPC from infinity to the point against to the electrostatic force of the field. Condition apply. Here we have underlined the word without acceleration. What is meant by without acceleration? The work done, if you recall the first PUC definition, that is work done is nothing but force into displacement. In that displacement, displacing, that means what? Displacement should be, means what? It is shortest distance between the 2 points. That means what? It should be free from acceleration. That means it should move with a uniform velocity. Then only it is considered as work done. So that means, I repeat once again the definition of electrostatic potential. It is the total work done in carrying or bringing a UPC from infinity to the point against to the electrostatic force of the field. Let us write the equation. So if I write the equation, how equation will go? What they said here? Work done by the UPC, W by Q. Very simple form. Work done by the UPC itself is termed as electrostatic potential. The symbol of electrostatic potential is V. So look at this. V is equal to W by Q. Work done by the UPC is nothing but what? Electrostatic potential in a very simple manner. And let us write the SI unit of this electrostatic potential. The SI unit of work done is Joule, and the SI unit of charge is Coulomb. So that means what? Joule per Coulomb. Joule per Coulomb. It is also termed as one more word is there, that is volt. The SI unit of electrostatic potential is Joule per Coulomb or volt. So now let us define 1 volt. So SI unit is, then definition. The SI unit of electrostatic potential is Joule per Coulomb or VOLT, small volt or capital V. Just is a method to denote. Then the definition. So if I write the definition, how to write the definition of the 1 volt. So let us see the friends here. Substitute everything equal to 1 here. Here W is there, work done, charge is there, Coulomb is there. So now, suppose I will write here, if work done is equal to 1 joule, charge is equal to 1 Coulomb, then V is equal to what? 1 volt. Then how to define this one? 1 joule of work is done in bringing 1 Coulomb of charge. Again, from where we are bringing? From the infinity to the point. So that only I am writing here. So 1 joule of work is done. 1 joule of work is done in bringing a UPC or in bringing 1 Coulomb of charge, 1 Coulomb of charge from infinity to the point, against to the electric field, is called 1 volt or capital V. So it is denoted by capital V or else small v volt or capital G capital C raised to minus 1. So I repeat the entire definition once again. Suppose if I put work done is equal to 1 joule, charge equal to 1 coulomb, and then then V is equal to 1 volt. So that means 1 joule of work is done in bringing 1 coulomb of charge from infinity to the point against the electric field is called as 1 volt. Now recall the same definition or equation in another way. So now let us see here, a charge plus Q is there, point charge. So now I have placed the UPC here, UPC is here at infinity. Then see, this is quite important and very very important too also. Let us see what I am doing here. Let me consider one point. Already I have brought this UPC from the infinity to the point and placed at a point, say now A. Work is done. Afterwards, I will move the UPC which is here at the point A from A to B. What happened here? Look at this. This is the direction of the electric field. I am coming from that side, that means opposite or against to the direction of the electric field, and I am just displacing the UPC from point A to point B at a very small distance, say now dx, very, very small distance. What happened here? Here also work is done, but it is not the total work done, it is the small work done. Small amount of work is done in bringing UPC from one point to another point. I repeat once again, small amount of work is done in bringing UPC from one point to another point is called as, at point A there is one potential called as VA. This V only, I am taking VA because the potential is represented by V. When I bring the UPC from point A to point B, there is another potential called as VB. Then if I take the difference between these two potentials, and that itself is termed as a potential difference. Then the next term is potential difference. Potential difference, and this is also represented by capital V only. What exactly is the definition of this potential difference? Same again. Small amount of work is done. Small amount of work is done. Work is done in bringing a UPC from one point to another point. Condition here again same thing, without acceleration. Is termed as potential difference. So now if I write the equation for this, so now V is equal to VA minus or VA difference VB, that is equal to dW. Why I am writing dW means small work is done, dW divided by unit positive charge Q. Again, the SI unit of the potential difference is volt in volt. The potential difference is measured in terms of volt. The SI unit of potential difference is very, very important. The same potential difference is measuring in our day-to-day life. The potential difference, whatever we are measuring, same in naming volt, 220 volt, 240 volt, that is all this potential difference only. Right? I repeat the definition. Potential difference V is defined as small amount of work is done in bringing UPC from one point to another point against to the electric field. So V is equal to VA difference VB, that is dW by Q. It is measured in terms of volt. Then if I write the SI dimensional formula for the electrostatic potential or potential difference, it goes like this. Right? dimensional formula. So dimensional formula for potential difference is m l minus 2 a raised to minus 3, sorry, L2 a raised to minus 3, MLT, right, MLT raised to minus 3, a raised to minus 1, ML square t raised to minus 3, a raised to minus 1. This is the dimensional formula for potential difference. Now let us go to the very, very important derivation of this topic, of this chapter, that is, calculating the potential at a point due to a point charge. Very, very important for 3 marks. Potential due to a point charge. Very, very important derivation. Potential due to a point charge. Friends, in the first chapter we studied the force between 2 point charges using Coulomb's law, that is F is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R square. And already I said only one charge is producing the electric field, and that is given by F is E equal to 1 by 4 pi epsilon naught Q by R square. Now we are studying now what is the value of V, that is V is equal to. So for this we need to consider a point charge, say Q. So let me draw the diagram step by step. Consider a point charge Q at O. First sentence, consider a point charge Q at O. Now, after considering this, I want to calculate what is the electric potential at the point P at a distance of, say, R. Our motto is, what is the electric potential at this point P due to this charge plus Q. OP is the radial distance or radial vector R. Now, our same procedure. What is the electric potential? Electric potential is nothing but the total work done in bringing the UPC from the infinity to the point against to the electric field. Now the UPC is here. UPC is here at infinity. So now I have to bring the UPC from the infinity to the point. So once while bringing, I will consider an intermediate step. So now just I will extend. Assume that this is an infinite distance. This is infinite distance. While bringing this positive charge from the infinity to this point P, I will stop. I will take a pause at the point, say, A. So now at point A, I will place the UPC. The distance between the point charge and the intermediate place, say now A, and that distance is now x. I will call this distance as x. X, right? Now the UPC is here. The force, the electrostatic force between the charge plus Q and the UPC is given by F is equal to 1 by 4 pi epsilon naught into q divided by x square. Be careful, this is now x square. What the small q indicates? Small q denotes here UPC. So since we know that q is equal to plus 1 coulomb of charge, so then if I rewrite this one, I'll get F is equal to 1 by 4 pi epsilon naught into q by x square. After this, suppose instead of placing the point charge at A, if I move a small little distance from point A to point B, now the UPC is here, present UPC, at a small distance of say dx against to the direction of the electric field. So now UPC is coming in this direction, please keep it in mind. So now if I move a point charge from A to B against to the direction of the electric field, just a few minutes back I explained what is that concept. That concept is termed as potential difference. That is also work done. Small amount of work is done in bringing a UPC from point A to point B against to the direction of the electric field, and that work done is given by small amount of work is done. Small amount of work is done in bringing a UPC from A to B. That is dW is equal to vector F dot dx. Why I have taken the dot product here? Because it is a convenient way to solve one thing. Second thing is, it is very, though the work done is independent of path, for convenient method I have taken straight line, and the electric field is in this direction, I am coming in this direction, so both are in the opposite direction. Hence the dot product between them becomes f dx cos theta, angle between them becomes 180 degree. Then if I substitute here, so I will get dW is equal to say now this is 1, no? 1. So now minus F dx, that is equal to minus 1 by 4 pi epsilon naught q by x square into dx. This is a small amount of work done in bringing the UPC from infinity to the point against the electric field. But I am really interested to calculate the total work done in bringing the UPC from the infinity to the point P, not to the intermediate step. This is the only intermediate work done. So if I want to calculate the total work done in bringing the UPC from infinity to the point P, that I have to integrate. Okay, the total work done in bringing a UPC from infinity to the point P is given by, that means what? I have to integrate this equation. How to integrate this? W is equal to integration of dW. Then to integrate, I must have the lower limit and the upper limit. What is the lower limit? Our beginning point. What is the beginning point here? Infinite. Infinite is the beginning point. Where we are terminating our work done? We are terminating our work done at point P, at a distance of say R. So hence I have to write here R. So that means what? I have to integrate this equation number 2 between the limits infinity to R. Then if I substitute here, I will get, so integration between the limits infinity to R minus 1 by 4 pi epsilon naught into q by x square into dx. So now common terms I will take outside. Minus 1 by 4 pi epsilon constant, q is also constant, so 1 by x square and dx also variable, so I will keep inside. The remaining terms I will take outside. So 1 minus 1 by 4 pi epsilon naught, and q is also taken outside. So inside bracket we are left with infinity to R 1 by x square into dx. This is of the form x raised to n. So now we know that So integration of x raised to n dx is equal to n into x raised to n plus 1 divided by n plus 1. This is the term. So now I have to substitute this value. If I substitute here, what I will get? So this is x raised to minus 2 dx. That is nothing but x raised to minus 2 plus 1 divided by minus 2 plus 1. This becomes x raised to minus 1 divided by minus 1. This becomes minus 1 by x. Substitute here. So if I substitute here, I will get w is equal to minus q divided by 4 pi epsilon naught. After integration, we have arrived at the value minus 1 by x between the limits infinity to r. First, we have to substitute the upper limit followed by the lower limit with the minus sign. So now w is equal to minus q divided by 4 pi epsilon naught into minus 1 by r. Minus of minus becomes plus by 1 by infinity. The value of 1 by infinity is 0. So we are finally left with only minus 1 by r. If I take minus on outside, minus q by 4 pi epsilon naught into minus 1 by r. Take out inside. So now we will get w is equal to 1 by 4 pi epsilon naught plus minus minus become plus, then q by r. So now just if you recall the definition of the work done or the potential, electrostatic potential is nothing but the work done in bringing the UPC from the infinity to the point. So now the electrostatic potential and the work done are both are same, one and the same. So from the definition, V is equal to plus or minus 1 by 4 pi epsilon naught q by r is the final expression for the electrostatic potential, because we know that electrostatic potential is nothing but the work done. Why I wrote here plus or minus for potential? Here is the reason. So potential is positive if the source charge is positive, potential is negative if the source charge is negative. Thank you.